Hello everyone and welcome. Today we are bringing to you the webinar on revealing shapes, particle morphology hints impurity rejections during API crystallization. As usual, my name is Carmen Guguta. I'm your host from Technovis Crystallization Systems. And today together with me, I have Dr. Jochen Schöll from MSD. Most probably know our Crystal 16 and crystalline, and most probably you already have a Crystal 16 or a crystalline or even both of them in your lab. For those that do not have one yet, and after this webinar, they realize that maybe they would like to try one of these instruments to try to solve one of your problems, please feel free to contact us, and we will try to make it possible either online or physically into your lab to bring a demo of a crystalline or a Crystal 16. Please remember, Crystal 16 is the instrument for solubility, metastable zone with any type of solid state screening, crystalline with the camera technology that works exactly like a microscope, and with the Raman helps you to develop or optimize your crystallization process or even your formulation process.
Jochen Schöll, and today's talk is on revealing shapes and how particle morphology can hint impurity rejection capability during API crystallization. MSD is a global pharmaceutical company, as most of you might know, and headquartered in New Jersey in the US. However, I'm based, or my site is based here in Schachen, outside Lucerne, in very scenic Switzerland. It's a place I came dearly to over the last 9 years. And when I started here, one thing that really struck me positively was a quote of George Merck that he stated, "Medicine is for the people, it's not for the profits." And he said this like at a time when actually my father was born, so quite a while ago. But still, this is something like a core motto of our company. And I think with the current pandemic going on, it's also something that the pharmaceutical industry entirely has come more and more to kind of appreciate. With this kind of core objective of my company and also the pharma industry, I want to step further and kind of come to the main points when it comes to pharma crystallization. So everyone involved in the crystallization of drug substance, he's aiming literally at three things. One is to ensure the crystal form, to get typically the most stable crystal form, to ensure shelf life, nothing's happening with the drug product. Inside the drug product, nothing's changing. So it's a thermodynamically stable form. Then we're looking at the particle size to ensure the API has the right bioavailability for the body, such that the concentration in the bloodstream is the desired one. And finally, there's purity. So the API purity needs to be there, since we want to provide API and nothing else, ideally. And the main task is literally to come up with a process, a robust process, that is the solvent system, an ideal solvent system in which the API is stable, but I can still provide a good yield process. Run the process at temperatures that are ideally as benign as possible, and then figure out the addition rates of anti-solvent or whatever to come up with a robust process that not only works in the lab, but also then is transferable to larger scales, and ideally even among different sites once the drug gets produced in different places. So, but early on in the development of an API, I typically face the challenge that there is only a limited amount of API available. Every project that's coming on is really new. So there is a new API, a new molecule that we're making, that the chemists are putting together, and then it's initially at very small quantities. So when it comes then to crystallization development, there is just like not a lot of material around. And there are three ways literally to make most out of it. One is obviously miniaturization. So we reduce the size of the reactor such that although we work at very small scale, at small quantities of API, we still get an as mostly representative outcome of the process. And typically this is like already with stirring, this becomes an issue because once you go below a certain scale, overhead agitation is not, or is rarely available. And once you turn to magnetic stirring, obviously the particles are under constant crunching of the magnetic stir bar, and the outcome is not that you would have as of overhead stirred reactor. With this, to make most of it, comes then parallelization. Once you have like smaller reactors, you can like run several experiments in parallel to study process conditions, solvent combinations, etc. And finally, the third pillar is really for us data-rich experimentation. So every single experiment, ideally, we want to have time-resolved information from both liquid and solid phase to understand both kinetics and thermodynamic events better and faster, such that our process development also time-wise speeds up. So for us at MSD, we have kind of the following approaches that we've come to, like for miniaturization and parallelization at small scale. We're using here the crystalline system, a system which provides overhead stirring, which provides anti-solvent addition with external pumps and temperature control. And we've combined this, or the system allows also to have like an imaging as well as a turbidity probe. And we've also the possibility to use a Raman in case there are like form questions or solid form questions. So this is something that starts at 2 to 6, 2 to 8 milliliters and works pretty well. And I've been using this for this project extensively. Once we go to larger scales, we have like automated lab reactors as shown here on the right-hand side at the 100 mil and the liter scale. And here we have the possibility to use in situ probes to characterize solid phase using the FBRM, which then produces the chord length distribution, which depends, or which is a function of particle count and particle dimension, as well as the PVM, which is an in situ microscope. And we're using an ATR FTIR here to characterize solid concentration as a function of time. There's an additional Raman, which is not shown, but that's kind of the workhorses we're using for our work. Now, coming to the kind of today's system I'd like to present, the issues here, I've started joining this project just after the first GMP delivery, so there were 1.5 kg of API available. And you have to imagine that, there are like a lot of demand for this material. There are tox studies that need to go on, stability studies. There's formulation development for further clinical runs then. And so the crystallization group is kind of in line to get their fair share. And looking at the first GMP delivery, there were a couple of things that needed improvement. Initially, the process was based on a solvent switch crystallization. So the API was dissolved, or the reaction stream was dissolved in ethyl acetate, and then was solvent switched into toluene. And although it successfully rejected impurities, which was like already a good sign, it failed controlling the solid form. So there were 2 different polymorphs, as I will show later, and an additional recrystallization step was needed from water methanol. And with this, then the crystal form was a pure desired form was achieved. And then finally, the API needed micronization, which was performed as spiral jet milling, and the whole process then yielded about 1.5 kg of this API. As you can see, like this rhombic particles shown on the upper micrograph with about an X50 of about 80 microns, they were then milled down to an API size of about 4 microns, so a factor of roughly 20. And you can see this. Now, looking at kind of what have I done then starting on, or what was been done, one thing that we typically do is really get solubility data for a broad variety of typical solvents in a high throughput manner. So here we have like a robotic system which provides in a 96 well plate format, then provides solubility in different solvents, in solvent mixtures, all at room temperature, along then with solid form data if something was crashed out or was analyzed, which is not shown here. But so as a first impression here, I've kind of, to facilitate all this data a bit, I've highlighted in green the good solvents, in red the good anti-solvents, and also if there are systems to avoid, since there might be risk in there. Green, which is good, like a broad variety of solvents, both polar and apolar systems. So we can work from acetonitrile water, for example, which is interesting since there is also like a solubility bump here at 90-10 acetonitrile water compared to the pure acetonitrile. There are the high boilers, for sure. We want to stay out of them for the moment. And then there are also 2-methyl THF, ethyl acetate, and others, which could be then combined with heptane. THF and acetone I've highlighted here in combination with water, at least, as a risk. Why? Mainly because the solubility is very elevated, even in 80-20 mixtures between THF and water. Same here for 90-10 acetone water. And then it drops very steeply for here 50-50 THF water below 1 mg per mil. Same here for 80-20 acetone water. This is something that occurs oftentimes and indicates solid liquid-liquid separation, so an oiling out phenomena. And this is why these systems kind of were not further studied in detail. We've already touched on this point. The API has 2 known forms, so there are 2 anhydrous forms. Initial seeded lab crystallization runs were performed both in a apolar and a polar system, here ethyl acetate, heptane, and acetonitrile water, and both were successfully kind of generated the desired form too. So this all looked good for the moment. Now, when then these results were performed, like these runs were performed at the 300 mg scale in the crystalline. One thing that was like particularly, suggestive in a way, was that the apolar systems, as you see here, ethyl acetate heptane, ipacaptane, both of them generated, particles of a certain width broadness or widthness. So they were like less flat, not as flat as acetonitrile water, where you here see on the right hand side particles that you would rather maybe characterize as platelets. So there was like a distinct difference in morphology, and this was where the question came up, like, so is there maybe potential for different impurity rejection as well? These experiments, these initial experiments, these were performed with pure API. So this was API that was going into GMP formulations, and so the impurity rejection could not be tested back then. But there was the question, like with these morphology differences, is there something that once coming with a reaction stream, is there maybe difference in impurity rejection capabilities here? And this topic of impurities in crystallization is a topic that has been treated already for quite a while in the literature, so there's quite a lot around. Starting back before actually I was born, Davy and Mullen in 1974 looked at ammonium dihydrogen phosphate, ADP, crystals, and characterized the impact of chloride salts on the velocity, on the growth velocity of different facets of the crystal. And this was later then modeled even by Kubota and Mullen. And so the possibility of having impurities adsorbed to specific crystal surfaces or crystal faces is known since quite a while, and more recently there's been a nice guide for the practitioner, I would say. This is from CMAC in the UK in combination with a couple of industry partners, and they've presented a structured approach to cope with impurities. And they make not only a nice overview between the different possibilities on how impurities can be trapped between inside an agglomerate, inside the particle, inside the crystal lattice, but also on the surface, absorbing to it. But also then, they've developed kind of a pathway on how to identify which of these phenomena is actually occurring, and with them the strategies to get rid of these. And finally, a paper from 2005, which has been published in a book on advanced topics in crystallization, which I liked a lot in preparation of this talk, was the crystallization of phenacetin from a reaction mixture. And there, the impurity of raw starting materials, in this case paracetamol, was very well studied in terms of both on different solvents and how they change shape, as well as on how different concentration of the impurities can have an impact on morphology. So with all this literature, what does this mean for our development work here further? Again, we've seen this from early on experiments with pure material. Once I ran this with crude material, I've received kind of the following results. When it comes to API purity, indeed, the apolar systems had a very good impurity rejection capability, which resulted for both systems actually, ethyl acetate and 2-methyl-THF-heptane achieved 99.9% LCAP, high API weight percent, whereas acetonitrile water clearly couldn't meet these levels and remained below 99% LCAP and could not achieve these impurity rejections. So our kind of initial presumption proved right, which is good. Interesting was that form control appeared to be an issue for ethyl acetate heptane, which gave a mix of forms here, which I will explain further in a couple of moments. Another issue at, let's say, this scale, at least at the beginning, was like that the color rejection was insufficient. So the incoming crude material was brownish, and the crystallization in all of these solvent systems managed to produce something grayish, which then sometimes can be an issue for drug product manufacturing. So ideally, we want to have really something white. And looking now first at the ethyl acetate heptane system. So here we have like a data-rich experiment at 3-gram scale. And what you can see is on the upper part, you can see both process data. There is the temperature profile from left to right in red, as well as the heptane addition in blue, alongside with FBRM counts per second below 10 microns. So it's kind of the number of fines in the process, as well as the solute, not the solute concentration, but the IR band, which kind of should correspond in a way to the solid concentration. And on the lower hand, you see micrographs from the process using the PVM. Interesting here that the jet milled seed initially, doesn't really seem to have an impact, at least on the solid concentration. There's not a lot going on, so the supersaturation initially was maybe a bit too low to really provide growth. However, still there is a bit of supersaturation since the particles visually already start agglomerating here. So that's what you see from the jet milled seed added to the end of seed age. And once we start then adding the heptane over time, initially we see a drop in what corresponds to the solid concentration until it rises again. And there I have to say, this is more of an artifact. So there's particles or something else forming on the probe window, and therefore kind of making this part of the signal not really useful until after the overnight crystallization in the morning. I wiped the probes, and that's kind of where the actual solid concentration at that point decreased to. Similar for the F-barium, there was also a bit of probe coating going on, as you see in this drop here. However, we see in the particle or in the visual information down here, there was a bit of growth, a bit of agglomeration, so the process kind of was going on until in the last image, there's also something elongated here, and that might be then what we see here, that there were some larger particles actually from form 1 generated. This obviously undesired and rather late in the process. So the question is, where does this come from? Yield, volumetric productivity, cycle time, all values that are acceptable, but where have this form impurity, where did this come from? And looking at the process helps in this case, since what has been formed here was at the hot reactor walls, particles kind of formed from splashing all over the place, and then was creeping up. And this is obviously something we can analyze what has been formed on the reactor wall, and this was a mix of the two forms. And once this then grows and falls back in, you kind of get a late stage seeding of the undesired form, and that's kind of where the undesired form comes from. So crust formation is definitely an issue here. At manufacturing scale, typically this is less of an issue since there is a bottom heating only, so there are no hot reactor walls, and they're kind of continuously washed by solvent that's condensing at the upper parts of the reactor. However, at lab scale, I can mimic this and lift the reactor, so I have just like a hot bottom heating. However, the steel probes, they kind of show, as you see here, a similar effect. So the crusting is something that, ideally we need to take all out and work with either a glass lint or a Teflon lint reactor shaft, and then we kind of can overcome this issue here. So much for the form. Form control then should be kind of achievable. But what about the color? So you see the crude API here on the left-hand side, and what has been done then was literally we've used activated carbon to kind of absorb anything that's undesired from a color perspective, and obtained nice white pure API on the right-hand side. So with all these issues kind of solved, let's look what happened during the second GMP delivery. So first of all, my chemistry colleagues haven't been lazy. They've improved the process as well, and reduced raw material cost by a factor of 40, which was very good to see, since there's like a 27 kick, and also for future upcoming deliveries, then there's a clear cost advantage. The improved API crystallization process was able to eliminate the need for crystallization due to the improved impurity rejection, and ultimately we have like obtained a very pure API in combination with the activated carbon treatment. And the form control has been improved via the process development work and an optimized seeding strategy. And so we've managed to kind of lower the seed mass, but then have like an extended seed age to optimize for this, and delivered 27 kg of API with a improved crystallization yield only of 13%. This was jet milled again to give the required particle size. So something that I'd like to point out, which is kind of still ongoing, the question if we can eliminate jet milling. So I've started here with a small scale preliminary testing. If we can, in a high shear environment, we can generate the particle size and form control required. And from the initial experiments, it doesn't look like that. Again, I've looked into acetonitrile water and ethyl acetate heptane to see if I can, by adding an API solution of 100 mg per mil into anti-solvent at a high shear environment, if this works in terms of like providing the required supersaturation to achieve nucleation rates that allow then the required particle size below 10 microns. If this is something achievable, and at the moment, I'm not very convinced, but I will give it a couple of more shots at higher, at elevated still supersaturation. However, the main issue that might be, and that's visible actually in both systems here, is that at least in these unseeded experiments that I've started here, obviously you get concomitant nucleation. So both forms nucleate at the same time and then start growing. So there is not the required form control to obtain the desired API form only. So that's kind of work ongoing. With this, I'd like to provide a quick summary. So the different particle morphologies, as shown, they had indeed, in this case, have highlighted differences in impurity rejection. So with lower aspect ratio here correlated with higher purity. And the combination of the miniaturization and data-rich experimentation allowed for optimized process design regarding impurity rejection, form control, decoloring, and the final process yield. And hopefully the further work on a bottom-up process, will still yield some fruit. And with this, I would very much thank you for your attention. I hope you enjoyed what I presented. And I'll acknowledge all my coworkers' help and try to answer any questions that might come now. Thanks.
Thank you very much, Jochen. We have a few questions I would like to read to you, but before that I have myself a question, maybe a bit related to the crystalline, and because you were saying in the beginning about this miniaturization, and actually I liked it quite a lot, and this is actually what you see a lot in many labs around the world, I must say, how you go from actually small scale to larger scale. What was actually, if you can once again emphasize the added value of having this, for example, the crystalline, these small reactors, 8 reactors in parallel, how made your life easier, let's say, in this specific case?
I mean, to me, the crystalline is really helpful, not only because it allows, it gives me the possibility to have like use very limited amount of material and get a lot of experimental results out of it. But it's also in terms of like ease of use, it's very, I like it a lot since it's very, like in a matter of an hour, I can kick off 4 to 8 experiments just like this. So it's very productive, very efficient, And as said, in that scale range, to me, it's kind of a unique possibility to work in, and also the possibility to follow then with the cameras what's going on in the process is really, really marvelous to me. Simply to follow what's going on in there without having to sample, without the risk of from sampling to the microscope something changes, and with such limited quantities, it's also it's hard to sample. So everything I can measure in there, it's better.
And what is exactly the type of data that you are saying that you make use of? Is I think the cameras you just mentioned. Anything else that? What do you get out of it? So much data.
To me, it's more the camera. I mean, there is also the turbidity, which is kind of following what's going on, but it's almost like the camera is also like a built-in turbidity meter for me. And sometimes then when we know we have issues with form at that early stage, it's also helpful to hook up the Raman, but it's more the camera that I'm using.
Okay.